Time to pull it all together. Returning for the last time to Brady and the CSO team, let's revisit the pod from Amy's developers that failed to deploy it in the introduction to this hands-on material. We understand at this stage what the problem was. Essentially, the default SCC in the service account available to the cluster did not grant the level of permissions requested by Amy's application as part of her SC in the YAML-based deployment manifest. Brady will need to examine the elevated privileges that Amy's application requires, determine any potential risks that they might pose to the cluster, and then recreate the deployment using the custom SCC that he creates and the service account that was crafted earlier, later assigned to Amy's pod. First, copy and paste the following YAML file into a text browser, saving it as deploy.scsa.yaml to your desktop, or download the YAML file directly from the following GitHub repository that's linked in your documentation. Open your terminal window connected to the OpenShift cluster via OCCLI and issue the following command to create the deployment. Recall that earlier in this hands-on material, you create a customized SCC to validate the requirements outlined in Amy's SC or deployment manifest request. We've now just deployed a new application with similar permission requests in the SE, but utilizing the new service account and therefore the custom SCC that Brady's team made available to the cluster earlier. Are the results different from when the pod failed to deploy the first time? Let's find out. First, we need to retrieve the details about the pod by reviewing the full YAML description. Pay particular attention to the annotation that shows what SCC was used, the container security context, and the pod security context. Verify for yourself that the new deployment used the SCC tutorial SA service account that Brady set up earlier. Using your terminal window, issue the following command to retrieve details on the pod and have them output to screen with YAML formatting. Alternatively, we can check the same results using the OpenShift web dashboard. Return to the dashboard and toggle the perspective switcher to the administrator role. Drill down from the left-hand menu into Workloads and then Deployments, and locate scc-tutorial-deploy-se-sa from the list. The status to the right of that item should say one of one pods are currently running. Click on the one of one pods text to open the deployment details page. From this page, click on the name of the pod, which would look similar to scc-tutorial-deploy-se-sa, followed by a string of uniquely generated characters. Once you click the name, select the YAML tab from the top of the screen. There are several lines of interest for us to inspect in the deployment YAML details. What is the value and name assigned to the OpenShift.io/SCC field? You may need to expand line 30 by clicking the greater than sign to the left of the managed field line to reveal this. What is the value of service account name on line 146? What is the range of values under security context, specifically for supplemental groups? What is the value of FS group on line 175? What is the security context values for the container? Reference of values assigned to run as user and run as group on lines 169 and 170. Let's test the runtime permissions of the container to validate that the pod and Amy's containerized application within it has the correct levels of access and privileges. Return to the terminal and issue the following command to retrieve the name of the pod. Next, use the terminal window to create a remote shell connection to that pod's container. Do so by issuing the following command, replacing the pod name with the name retrieved in the previous step. Via the terminal window, now connected through a remote shell to the OpenShift pod, let's check the user ID and group permissions assigned to the pod. Enter the following and check the results. The output returned screen should show that the pod is using the user ID or group ID that was specified in Amy's SC deployment manifest. The supplemental groups that were requested as part of the SC have also been created, and the pod user is now a member of those groups. Finally, the pod and user is now also a member of the file system group, which was specified using the security context.fs group field in the manifest. Now let's test what happens when writing a file. Issue the following commands to write to a file on the volume. Then attempt to write a file to the temp directory. Next, try to write a file in the root directory. And lastly, check the permissions on all the files which we created. From the results printed to the screen, we can readily see that the file created in the temp directory is owned by 1234 and 5678, which is the user ID and group ID specified earlier. On the volume, the file we created is owned by 1234 and 5554, once again the user ID and FS group that we specified in place of the project default that was done in a much earlier module. Brady, in executing these instructions, still did not have root level access to the pod, and therefore attempts to run as root and use the root group failed. However, that failure is not unexpected. After all, Brady never intended to grant any requesting pods root access via the custom SEC that the security team devised. Much to Brady's delight, all the protected Linux functions that the containerized application had requested earlier performed exactly as expected. The custom SEC defined by the CSO team and Brady worked splendidly well, and the CIO team's application is now performing both as planned and in a secured and trusted fashion.